All right, in this video, I'll be starting chapter 9. In chapter 9, we will be going over these topics, parametric equations, polar coordinates, and conic sections. Okay, let's start with section 9.1, the first section in this chapter, parametric equations. Okay, so basically in this section we'll be formally defining what we mean by a parametric equation, and also we will be plotting the graphs of some parametric equations given to us. Okay, all right, I want to start with this definition, definition 9.1, parametric equations in two variables. Okay, here is how we define a parametric equations in two variables. Parametric equations in two variables are a pair of functions x is equal to f of t and y is equal to g of t, where the parameter t is defined on an interval I of real numbers. And then here is what we mean by a parametric curve. A parametric curve is the set of points in the coordinate plane. This is the set of points, okay, x of t comma y of t for t in the interval I. Basically, you collect all the possible coordinate pairs x of t comma y of t so that your t is in the interval I. Okay, that collection of coordinate pairs is what we call a parametric curve. Okay, again, parametric equations in two variables are given by two equations of this form: x is equal to f of t and y is equal to g of t, and a parametric curve on the coordinate plane is a collection of coordinate pairs where you pick your t always to be in the interval line. Okay, all right, let's move on and work on an example to understand this definition. Here is the example that I want to go over. Sketch the parametric curves determined by the following parametric equations. Okay, as you can see, this clearly has the form of two parametric equations, right? It is just like this: x is equal to f of t, y is equal to g of t. Here you have x is equal to cosine t, y is equal to sine t. This looks like your f of t and this looks like your g of t, right? So all that is good. Okay, so how do we sketch the parametric curve determined by these two parametric equations? Well, we are going to do some trigonometric calculations here to find a relationship between x and y, and hence to find the Cartesian equation for the curve. Okay, so what I'm going to do is I'm going to use trigonometric identity. We all know that cosine squared t plus sine squared t is equal to 1, right? That means by Pythagorean theorem, let's work on part A first. By Pythagorean theorem, we have x squared plus y squared is equal to 1, right? That's because x is cosine, y is sine. X squared plus sine squared means cosine squared plus sine squared. We know that that is equal to 1 by Pythagorean theorem. Okay, so we have x squared plus y squared is equal to 1. Now we know that since x squared plus y squared is equal to 1 on the xy plane, we know that our curve has to lie on the unit circle. If you plot x squared plus y squared is equal to 1, that is the unit circle, right? So that means this curve should lie somewhere on this unit circle. It could be something like this, or it could be the lower half, or it could be the side like this. Who knows? Okay, we need to figure that out. Okay, how do we figure out which half would this curve specify on the interval 0, pi? Well, what we do is we plug in some points. Let's pick some points in this interval. Okay, I'll pick 0 and then pi over 2 and then pi from that interval. These are points. These are 3 points in this interval. I will evaluate the points on the curve at these specific points. When t is equal to 0, how do I find the point? I plug in t is equal to 0 in these two functions. That will give you the x comma y coordinate pair. Okay, so that point will be cosine 0 comma sine 0. That's the point. And then I'm doing the same thing for the others. I'm going to plug in pi over 2 next. Cosine pi over 2, comma, sine pi over 2. To find the corresponding point, because x is given by cosine t, y is given by sine t, okay? So I plug in pi over 2 in the parametric equations to find the corresponding point. And then when pi, you get cosine pi, comma, sine pi. Now we can evaluate these points. This is 1, comma 0, of course. The second point is going to be, what is cosine pi over 2, comma pi over 2? That is 0, comma 1. And the last point is, of course, minus 1, comma 0. We all know that, okay? Now we can mark these points. These points have to be on the parametric curve. The first point is here, clearly 1, comma 0. The second point is here, 0, comma 1, and then minus 1, comma 0. Looks like this is the upper half circle of this curve, okay? So looks like this is corresponding to the upper half circle of the curve. Now we need to figure out which direction this curve is moving as t increases. The starting t is 0, right? When t increases from 0, what happens to this curve? Would that be going this way, like this, or would that be going in the opposite direction, like this? We can figure that out easily. What you do is look at this equation and see what happens as t increases from 0. Okay, if you give a very small increment to t from 0, what happens to these quantities x and y? They are clearly positive, right? If you put a small t value here and here, both quantities are sine t and cosine t, both are positive. That means both x and y values are positive. That means our curve should be like this. It cannot be going the other direction like this. It should be going this way because both x and y are positive as t increases. Okay, all right. So that means the direction of the parametric curve should be like this. This is the parametric curve specified by these two parametric equations. This in blue. Okay, so I have marked that piece of curve in blue. It is basically the upper half circle of the unit circle going in the anti-clockwise direction. Okay, this is going in the anti-clockwise direction. Okay, that completes that example. Next, let's go over part B. Let me add a page. How do we actually I'm going to leave part B as an exercise, because here in the first part we were asked to graph this when t is between 0 and pi. In the second part we have the same two parametric equations, but t is between pi and 2 pi. How do you handle this one? Well, we follow the same procedure. In that case, you will see that your graph is, this time it's not the upper half circle, this time it's going to be the lower half circle. Okay, again you pick 3 points in this interval and plug in those 3 points. You will see that those 3 points are going to be, I'm talking about part B, okay, those 3 points are going to be this point, and this point. Okay, again you need to figure out the direction of this curve. You should be able to see that the direction is going to be again anti-clockwise. It is going this way. Okay, so I will let you verify that, and then let's move on to part C. In part C, this is exercise. Part C, we have x is equal to sine 3t, y is equal to cosine 3t. Okay, so how do we handle this? By the way, t is given to be between 0, 2 pi, closed interval. Notice that when t is between 0 and 2 pi, when t goes from 0 to 2 pi, the sine 3t and cosine 3t go through 3 periods because this coefficient is 3. Okay, you might want to recall some pre-calculus topics here. When you have this coefficient 3 and when t is between 0 and 2 pi, when t goes from 0 to 2 pi, the sine 3t and cosine 3t go through 3 periods. Okay, keeping that in mind, let's try to determine the shape of the curve is specified by these two parametric equations. I'm going to do a similar thing like in the previous case. notice that by Pythagorean identity, x squared plus y squared, that is sine squared 3t plus cosine squared 3t, we know that this is equal to 1. No matter what angle this is going to be, sine squared plus cosine squared is always 1. Okay, so this should be equal to 1. So that means this gives us the equation, Cartesian equation of this curve, x squared plus y squared is equal to 1. Again, we are going to get the unit circle, right? We have a unit circle. You get the unit circle again. What is remaining to figure out? You need to figure out where to start and where to end the curve. Okay, would that be going like this, or would that be circling around multiple times around this circle, or would that be 3/4 of the circle, and which direction will it be moving? Okay, those are the things now we need to figure out. How do we figure that out? Again, the procedure is same. Okay, so first we find the starting point. Well, let's see what happens when t is equal to 0. When t is equal to 0, what is my point? X is equal to sine 0, which is of course 0. Y is equal to cosine 0, which is of course 1. I'm just plugging t is equal to 0 here and t is equal to 0 here. Okay, so that point is 0, 1. 0, 1 is here. So this is the starting point. Okay, now we need to figure out the direction. Would that be going in this direction, or would that be going in this direction? Okay, it is very easy to figure that out. What you do is you check what happens when t is increasing from 0. Okay, what happens if you increase t from 0? Okay, quantity going to be if t is increasing? If you look at these two equations, what happens as t increases from 0? Okay, t increases from 0. What happens to these two quantities? You need to figure that out. Okay, notice that when t increases from 0, like think about this quantity is like t is 0.001. If you put t is 0.001 and 0.001 here, then you should see that both of these quantities are positive, right? Clearly, if t is a very small positive number, both of these quantities have to be positive. It's clear, because in the first quadrant, both sine and cosine positive. If both of the coordinates are positive when t is very small positive number, then it has to turn this way, right? There is no way that it is going this way. What happens if it goes this way? If it goes this way, your x value is negative. There is no way that your x value is negative for small positive t values here. If you have a small positive t values, this is a small positive value. For small positive value, sine is positive. So that tells you that our curve is going this way. Now all what you need to figure out is that how many times will it be rotating? Will it be rotating only 1/2, or will it be completing a full circle, or will it be going around the unit circle multiple times like this? It's again easy. We know that this completes 3 periods in this interval. For t in this interval, these two parametric functions complete 3 periods because this coefficient is 3. That means this goes around 3 times. First time, second time, third time. Okay, but I have to draw these circles on the same unit circle, but to make it clear to you, I drew it so that you can see the curves separately. Okay, so basically the curve goes like this 3 times on this circle. That's the curve. I will draw it in a different way so that anyone can see it. Okay, so it will be a curve like this. You complete a 1 circle, second circle, and then the third circle. That's the curve specified by these two parametric equations. Okay, that completes that example. Let's move on. Now we are down to the last part of that example. What is the last part? We are given again, this time it's a little bit different equation, but we have a trick there. Okay, 1 minus t squared over 1 plus t squared, and then y is equal to 2t divided by 1 plus t squared. Notice that t is given to be between 0 and infinity. Okay, t is given to be between 0 and infinity. Notice that if t is between 0 and infinity, these quantities would never be negative. Okay, it could be 0, of course. If t is equal to 0, this is 0, that's okay. But these two quantities would never be 0 as long as t is between 0 and infinity. Pardon me, actually this quantity would never be negative, but this quantity, of course, it could be negative. Okay, so keep in mind that your y is always greater than or equal to 0 as long as t is between 0 and pi. That will help 0 and infinity. That will help us to figure out the shape of the curve. Okay, so the first thing that I would like you to notice is that if you compute x squared plus y squared, that is this quantity squared plus this quantity squared, what would you get? I will let you verify that. You will get exactly 1 minus t over 1 plus t squared, whole thing is squared, plus 2t over 1 plus t squared, whole thing is squared. This is exactly 1. Okay, you should be able to verify that. I will let you do the algebra. Now again, this is the unit circle, right? X squared plus y squared is just the unit circle. Now we know that our curve should be on the unit circle, but we need to figure out which direction it moves and which region it specifies on the unit circle. Would that be this region? Would that be this region? Or would that be multiple revolutions like in the previous example? Okay, so how do we deal with this? Again, notice that when t is equal to 0, that's the starting point of t here. T is between 0 and infinity. When t is equal to 0, what is the point? If you plug in t is equal to 0, you get x is equal to 1, y is equal to 0. Okay, so the point is here, 1 comma 0. This is the point. Okay, this is the starting point. Now you need to figure out the in which half circle or which area your curve is lying. Clearly, your y coordinate would never become negative, right? As you can see here, when t is between 0 and infinity, this is greater than or equal to 0. So that means it has to be somewhere on this upper half circle. Okay, would that be the entire upper half circle, or would that be the half of the upper half circle? How do you figure that out? Well, to figure that out, what you need to do is you need to find the limit as t approaches to infinity of this quantity. Okay, that means you need to find the x coordinate. What happens to your x coordinate as t approaches to infinity? Because t is between 0 and 1, we know that the x coordinate is 1 when t is equal to 0. What happens to your x coordinate when t approaches to 0? You should be able to find that limit as t approaches to infinity, 1 minus t squared over 1 plus t squared is equal to minus 1. You just find the limit of the x coordinate. Okay, you find the limit as t goes to infinity, your x coordinate, that is exactly minus 1. Minus 1 is here. You know that, we all know that minus 1 is here. Okay, and also notice that limit as t approaches to infinity, the y coordinate 2t divided by 1 plus t squared, this clearly goes to 0. Okay, I will let you verify these limit statements. Okay, you know how to find the limit of a polynomial now. This is just a polynomial. You know how to find the limits. So verify that this limit is minus 1, this limit is 0. That means as t goes to infinity, your curve should be approaching this point, minus 1 comma 0, because this is minus 1, y coordinate is 0. Minus 1 comma 0 is this point, right? So as t goes to infinity, it should be going this way. Okay, we know that it approaches to this point as t goes to infinity like this, because this limit statement is true. Okay, so now the bottom line is our curve is this one. This is our curve, the upper half circle. It's an anti-clockwise curve. If the curve is moving this way, we say that it's an anti-clockwise movement. If it rotates other way, it's a clockwise movement. Okay, For example, in the previous example, we had a clockwise movement like this. I forgot to mark it there. So please understand that you need to have a clockwise movement here. Okay, that completes that example. Let's move on. Next, I want to go over this example, another example. Let's go over this. Sketch the graph of the curve described by the parametric equations x is equal to cosine cube theta, excuse me, y is equal to sine cube theta. Okay, so again, graph in parametric equations directly used in these parametric equations is straightforward. What you do is you make a value table. Okay, so here is how I am going to make the value table. Notice that both sine and cosine, since you have theta here, their period is 2 pi, right? So it is enough to consider the theta values between 0 and 2 pi. Because sine theta and cosine theta, they both have period 2 pi. So it is enough to consider the interval 0 to 2 pi. If I can plot the parametric curve on this interval, then it can be extended to any bigger interval using the periodic property of sine and cosine. Okay, so let me focus on this interval. In this interval, I am going to pick some special points. Okay, theta, my theta values would be, I pick 0, pi over 6, pi over 4, pi over 3. You should be able to answer why I am picking these special points. You should be able to see that, because these points, these are the familiar angles, right? We know the trigonometric values of these angles from calculus, pre-calculus 2. Okay, so I am picking those special angles, 2 pi over 3, 3 pi over 4, 5 pi over 6, and then I continue my table again. I next take pi, and then 7 pi over 6, so on and so forth, and finally I have 11 pi over 6. Okay, now what I'm going to do is, for those chosen special angles, I'm going to compute the x value. X value is given by cosine squared, cosine cube theta, right? So I can calculate cosine, I can plug in theta here. Theta value is 0 here. If you plug in theta 0 here, you get cosine cube 0, that is 1, right? We know that cosine 0 is 1. 1 cube is again 1. So you have 1 here. Similarly, next you plug in pi over 6 here for theta. If you plug in pi over 6, you get cosine pi over 6. You know the value of cosine pi over 6 from the trigonometric tables, and then you take the third power of that to find the answer. That will give you this answer. Likewise, by plugging all these theta values, various theta values, you can find cosine cube theta. And then, as you can see, you can complete this entire row. Similarly, you can complete this row to find the other cosine cube theta values corresponding to other angles. Okay, we do a similar thing for sine cube theta as well. To find the y coordinate, again you plug in theta. Theta is equal to 0 here. That will give you a sine cube 0. Sine cube 0 is 0. Okay, and then you plug in pi over 6 here. You know the value of sine pi over 6 from the table, and then you cube that value to get the y coordinate. Okay, likewise you can complete this table for all these angles, and then you can complete the second row here by following a similar procedure. That way we have a value table. Now what I'm going to do is I'm going to place these coordinates on the xy plane. Okay, here the x coordinate is 1, y coordinate is 0, that is clearly this point. I put a point here, and then the second point is 3 square root of 3 divided by 8 comma 1 over 8. I mark that point here. Likewise, I mark all the points given by this table. Then you should be able to see that you are going to get bunch of points on this plane like this. Okay, as you can see, this set of points on the plane suggests the shape. So the shape of the graph of the parametric equation should look like this. Okay, as you can see, I have drawn that over here. And which direction would that be moving? Clearly it is moving this direction. You should be able to see that from this value table. Okay, this is 1, 0. The next point is this point. That means it is this point, so it should be going this way. Okay, so this is the sketch of the parametric equations. A sketch of the curve given by the parametric equations. Okay, you should be able to sketch parametric equations following these steps. All right, let's move on. Here is the next example that I want to look at. Find the parametric equations that describe the curve traced by a point on the circumference of a wheel as it rolls along a straight path. Okay, so let's find the parametric equations that describe the curve traced by a point on the circumference of a wheel. Okay, let's say this is your wheel. This is the wheel and it has a fixed radius r. You know, when you roll this wheel, radius doesn't change, right? This radius, this length is always that length. Okay, I will take that length to be r. Okay, let's say your point that they are talking about, the specific point on the wheel is this one. Okay, so this is the starting. At the starting, when time is equal to 0, your starting point, this point is over here. When you keep rolling your wheel, your point is moving, right? It is moving like this. Okay, this point will be moving. Okay, so now what I'm going to do is, I'm going to take, at a given instant, I'm going to take this angle to be theta. The angle between this line, this perpendicular, and this line obtained by joining the origin and the point that you specified on the circle. Okay, this particular point. So this angle I'm going to take this angle as theta. Okay, now I'm going to parameterize the path of this point using this angle theta. Again, r is a constant. I'm going to parameterize this curve specified by this point using theta. Okay, how do I do that? At the end of the day, you will see that it's going to be your point will be going, this fixed point on the wheel will be going in a path like this. And then it will start again, so on and so forth. This is the picture given here. Let's see how we come up with that. Okay, all right, so how do we find the parametric equation of this curve specified by this particular point? For that, we need to find the x coordinate and y coordinate of this point for a given value of theta. Okay, so for a given value of theta, can you find the x and y coordinate of this point in terms of theta? Well, it's not hard. Okay, notice that if this is theta, and the radius is r, we know that this curve is r theta, right? That's pre-calculus. Okay, this is the arc length. Arc length of a circle is given by the formula r theta. That means because the radius is r, the angle is theta. Okay, so this length, this arc length is r theta. Do you believe that that is same thing as this length? Because you are rotating the wheel, right? This length should be same as this length because you started your point, placing your point here. This point was here at the beginning. At the beginning, this point was right here. Okay, then this length and this length have to be equal. Okay, so that means if this is r theta, this length is also r theta. That's why I have marked this length as r theta. Okay, now can we find the x coordinate of this point? Well, we need to do a little bit more calculation. Notice that if I complete this right angle, this is going to be the 90-degree angle. Looking at the geometry of this triangle, since this angle is theta and this angle is r, this opposite side should be r sine theta, right? Because you can write an immediate equation. If you take this opposite length to be y and that one r, you have sine theta is equal to opposite side divided by the hypotenuse, right? That is y divided by r. So y is equal to r sine theta. That's what exactly I have here. This y should be r sine theta. Okay. Likewise, similarly, you should be able to see that this length is going to be r cosine theta. Okay, now we can write an equation for the x coordinate here. The x coordinate is given by this total length minus this length. Would you agree with me? That is exactly the x coordinate, right? X coordinate is this length. This length is nothing but this total length minus this length. That is r theta minus r sine theta. x coordinate is given by r theta minus r sine theta. Can you tell me the y coordinate? Y coordinate is again easy. That is going to be, this is r, pardon me, this is what is this one? This is the y coordinate, right? This height. How do you find that height? We know this height. This height is r. It's a fixed number. It's the radius. So the y coordinate is going to be r minus this length. Okay, y coordinate is r minus r cosine theta. These are the parametric equations specified by this point as we'll move forward. Okay, so it will specify a path like this. All right, that completes that example. As I said, this will specify a path like this, and this is the path in the long run. Okay, it will when theta goes from 0 to 2 pi, it will complete one cycle like this. When 2 pi to 4 pi, it will complete another cycle, and so on and so forth. Okay, so how do you see that this this will be 2 pi? This full circle is 2 pi. It's easy to see here. When this point is over here, theta is 0. And then you increase theta, right? When this point is moving, when you keep rolling your circle, this angle will be increasing, and it will come all the way up to here. Okay, when this point come all the way up to here, somewhere here, when it touches the x-axis, it will complete a full 2 pi angle. Okay, full revolution. Full revolution means this angle will be 2 pi. Okay, so it will be like this. All right, let's move on. Next, I want to go over this definition, direction of motion and tangent lines. Definition 9.2, the slope of a parametric curve and tangent line to a parametric curve. Okay, so here is the definition. Let x is equal to x of t, y is equal to y of t be parametric equations for t in some interval I, and let t naught be a point in the interval I at which x prime of t naught and y prime of t naught both exist. What do you mean by x prime of t naught? Remember, x prime means, we introduce these notations. X prime of t means dx over dt. Okay, we are going to stick to these notions. This means x prime of t naught means the derivative of x at t naught. Y prime of t naught means the derivative of y at t naught. Okay, so we assume that these two are parametric equations in some interval, and t naught is a fixed number in this interval such that both of these quantities exist. Okay, then here is the conclusion. If x prime of t naught is not equal to 0, we define the slope of the parametric curve at the point x of t naught comma y of t naught to be m is equal to y prime of t naught divided by x prime of t naught. Okay, so the slope of the parametric curve at the point x t naught comma y t naught is given by this equation. Usually use the letter m for slope. Okay, slope is equal to y prime of t naught divided by x prime of t naught. And then this part tells you how to handle this if this x prime of t naught is equal to 0. This is valid when x prime of t naught is not equal to 0. But what happens if x prime of t naught is equal to 0? Then here is how you handle it. Okay, we define the slope to be m is equal to, this time you take the limit as t approaches to t naught, y prime of t divided by x prime of t. Okay, you take this limit to be the slope at this point x t naught comma y t naught if x prime of t naught is equal to 0. And then here is the second part. If the slope m is defined, if the slope m is defined in either in this equation or this equation, if the slope is defined, the tangent line to the parametric curve at the point t naught is given by the equation y minus y t naught is equal to m times x minus x t naught. This is an equation that you are familiar with, right? Given the slope and the point, you you know how to find the equation of a straight line. This is exactly what is about. Okay, so y minus the known point is equal to m times the slope times x minus the known x point. Okay, all right, to understand this definition, let's go over an example. Here is the example that I want to look at. Find the equations of the tangent lines to the cycloid given by these two parametric equations. Actually, these are the equations that we derived in the previous example. R theta minus R sine theta, R minus R cosine theta. Okay. How do you find the parametric equations? How do you find the tangent lines to this cycloid at the point theta is equal to pi over 2? Well, we apply this theorem. Okay, let's try to find the slope first. Before we, because to find the tangent line, I need the slope, right? Let's find the slope first. Slope is given by y prime of t naught divided by x prime of t naught. Okay, of course, in this case, your t naught is your pi over 2. It's the given value. Okay, t naught is pi over 2. You have to notice that first. What is x prime of t? Notice that in this case, the variable is not t. In our case, the variable is not t, it is theta. Okay, theta is the variable. So you need to find x prime of theta. What is x prime of theta? It is r minus r cosine theta, right? You just take the derivative of this expression with respect to theta. Similarly, y prime of theta is going to be, what is that? R sine theta. Okay, so those are the derivatives. Okay, all right. So now I'm ready to find my slope. Slope is given by, remember, x prime of, you need to plug in the point that you are interested in, x prime of pi over 2. Remember, in the definition, it is y prime of t naught divided by x prime of t naught. Okay, my t naught is pi over 2. This divided by y prime of pi over 2. This is equal to, I'm plugging here pi over 2. If you plug in pi over 2 here, we know that cosine pi over 2 is 0. You have r in the top. What do you have in the bottom? If you plug in pi over 2 in the other expression, you get just r. The slope is going to be 1. Because sine pi over 2 is 1, right? So it is r divided by r 1. So the slope is 1. We know the slope. What else do we need to find the equation of the tangent? Equation of the tangent is given by y minus y t naught times m times y minus y t naught is equal to m times x minus x t naught. We know m already. We need to figure out y t naught and x t naught. Let's do that. X of t naught, comma, y of t naught is nothing but, by the way, let me replace this t naught by pi over 2, because t naught is pi over 2. Okay, if you replace that, you plug in pi over t in this equation to find x of pi over 2, r times pi over 2, comma, minus r sine pi over 2, comma, to get the y coordinate, you plug in pi over 2 in the y equation, r minus r cosine pi over 2. Doing some simplification, you will see that this point is nothing but r times pi over 2 minus 1, comma, r. That means x of pi over 2 is this quantity, y of pi over 2 is r. Okay, now I can find the equation of the tangent. Equation of the tangent that we asked to find is given by y minus y t naught, that is r, is equal to m times, m is 1, x minus x t naught. X t naught is this quantity, that is x of pi over 2, x minus that quantity, r times pi over 2 minus 1. Okay, this is the equation of the tangent. If you want, you can write this in the slope intercept form, that is y is equal to x plus r times 2 minus pi over 2. Notice that this r is a constant. Okay, That is the equation of the tangent. All right, that completes that example. Let's move on. Let's go over another example now. By the way, another name for this m, you all know that is dy over dx. Okay, remember that. Slope is always dy over dx, if you want to call it. Yeah. Okay, now let's move on to the next example. Here is the next example that I wanted to go over. Find all points on the graph of the cycloid x is equal to r theta minus r sine theta and y is equal to r minus r cosine theta for theta in r, at which the tangent line is either horizontal or vertical, and find the equations of the horizontal tangent lines. Okay, first let me write the formula for the slope of the tangent line. Slope is given by m is equal to, if you want to say dy over dx is equal to, in this case that is going to be y prime of theta divided by x prime of theta. This follows from the previous definition. At a particular point t naught, the slope is given by y prime of t naught divided by x prime of t naught. At a general point, it will be y prime of theta divided by x prime of theta. That's the slope of your parametric curve. Of course, you can find this slope by differentiating your y. If you differentiate this y with respect to theta, you get sine theta in the top. And then in the bottom, the derivative of x with respect to theta is r minus cosine theta. Here it should be r theta. I'm messing this up here. R minus r cosine theta, and cancelling r in top and bottom separately, you get sine theta divided by 1 minus cosine theta. That is the slope or the dy over dx. Okay, now we need to find the points at which the horizontal tangent, at which we have horizontal tangents. When do we have horizontal tangents? Remember, we have horizontal tangents when m is equal to 0, right? The slope is 0 means at that point we have a horizontal tangent. For horizontal tangents, m is equal to 0. So if you set your m, this expression, to 0, what would you get? That is sine theta divided by 1 minus cosine theta should be equal to 0. This implies that sine theta is equal to 0. When does this happen? When is sine theta is equal to 0? When theta is an odd multiple of sine theta. Okay, so this, if you solve this equation, you will get theta is equal to an odd multiple of sine theta. Is an odd, not sine theta, pi, pardon me, multiple of pi. Okay, that means pi, 3 pi, 5 pi, so on and so forth. Okay, you have negative numbers as well. All right, that gives you the points where you get horizontal tangents. Okay, or in other words, you get horizontal tangents at these points: minus 3 pi, minus pi, 0, pi, 3 pi, dot dot dot. This dot 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 means you continue with odd numbers. Here also this dot 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 means you have minus 5 pi, minus 7 pi, so on and so forth. Okay, so at these points you have horizontal tangents. And now next question. Now the next question is, we need to find the points at which we have vertical tangents. What is the criteria for us to have vertical tangents? We have vertical tangents when your denominator is 0, right? Okay, whenever we have an undefined slope or an infinite slope, undefined slope, we have a vertical tangent. For a vertical tangent, you set your denominator to 0. Okay, for vertical tangents, we need a 1 minus cosine theta, that is the denominator of the slope, that to be 0. Okay, when the denominator is 0, it's undefined, you have a vertical tangent. Okay, so if you solve this equation, you should be able to see that the theta values given by this equation are the even multiple of pi. Okay, in this case theta is the even multiple of pi, even multiples of pi, pardon me, multiples of pi. Show this. Okay, this is homework for you. Okay, we are not done yet. We are asked to find the equation of the horizontal tangent lines. Okay, how do you find the equation of the horizontal tangent lines? Remember, the shape of this cycloid was like this from the previous section. The shape was like this, right? So how do you find these horizontal tangent lines? Basically, notice that we have horizontal tangent lines at these points, right? This at the same height. Okay, my drawing is not good. So how do you find this horizontal tangent line? To find that, I need this y value, right? So it has to be y is equal to something, right? Horizontal tangents are always y is equal to something. So to find that, I need to find this height. Can I find this height? Of course, yes. We know that the horizontal tangent occurs at odd multiples of pi. That means all what I have to do is to find this height. You plug in one of these numbers in the y expression. Okay. So in the parametric equation for y. So I'm going to plug in theta is equal to pi in this equation to find the y value. Okay. If I plug in theta is equal to pi there, let me add a page here. When theta is equal to pi, y is equal to r minus r cosine pi. But cosine pi is minus 1, so that will make it 2r. So the horizontal tangent is y is equal to 2r. Horizontal tangent. All right, this is the equation of any horizontal tangent lines. Okay. All right, that completes that example. Let's move on. Next, I want to define the arc length. Here is the definition. The arc length of a parametric curve. Okay, let C be a curve in the plane with parametrization x is equal to f of t and y is equal to g of t for t in some interval a comma b, where f and g are differentiable functions of t such that the parametrization is one-to-one function from the interval a comma b to the curve C. Then the length of the parametric curve C is given by this limit. Limit as n approaches to infinity, sigma k goes from 1 to n, square root of this quantity. Okay, and here this delta t, here as you can see, this delta t is defined by b minus a over n, and tk is equal to a plus k times delta t. This should remind you something. What does this remind you? This is the Riemann integral, right? Remember Riemann sums? So when we defined integrals, we defined integral as the limit of a Riemann sum. Okay, so this is somewhat similar to what we did in the Riemann sum section. So the bottom line is this limit is equal to the length of the curve on this interval when t is in this interval. Okay, and delta t is defined by this quantity and tk is defined by this equation, a plus k times delta t. All right, that is the definition of arc length. We will not be using this definition that much in this section, but we will be heavily using this theorem to find the arc length. Okay, let's go over this theorem. Let C be a curve in the plane with parametrization x is equal to f of t, y is equal to g of t for t in the interval a comma b, such that the parametrization is one-to-one function from the interval a comma b to the curve C if x is equal to f of t and y is equal to g of t are differentiable functions of t such that f prime of t and g prime of t are continuous on the interval a comma b. Then the length of the curve C is given by this definite integral from a to b square root of f prime of t squared plus g prime of squared dt. Okay, that's the bottom line. Again, we are not going to prove this theorem. We did a proof of similar theorem in calculus 2 to find the arc length. So this proof is also very similar to that. So we will not be going over the proof. Okay, so we will be looking at some applications of this formula to find the arc length of a given parametric equations. Arc length of a curve given by parametric equations. Okay, all right, let's look at this particular example first. Find the arc length of one arch of the cycloid traced by the point on the circumference of a wheel with radius r units. Okay, that is the portion of the graph of the cycloid that represents one full rotation of the wheel. Remember the wheel rotation problem that we were talking about? One full rotation means initially this point was here. Okay, when this point completes a one full revolution, this will go all the way up here and come back to the x-axis. Okay, then we say that it completes a one full circle. Okay, so it is started here. This point started its journey on the x-axis, and then we track down the path, and then we find when would that land on the x-axis again. Okay, that's what we call a full circle. This is a full circle. As you can see, this was the circles in the long run. Okay, it completes a full circle when theta goes from 0 to 2 pi. Okay, going back to our example. So how do we find the length? The length of the arc of the cycloid traced by this point on the circumference of a wheel with radius r. Or in other words, how do you find this length? We can use this previous theorem. Okay, the arc length is given by definite integral from a to b, this quantity dx dt. Okay, so what is a and b in this case? What is the parameter? Your parameter t in this case is theta. Remember, here we are using a parameter t, right? That t is same as theta in this case. Pardon me, your parameter t corresponds to theta in this case. Okay, in this example. So my integral will be, the arc length will be arc length is equal to integration. I have to put the lower limit, I have to put the upper limit, and then what do we have here? That is x prime t squared, f prime of t squared plus g prime of t. Notice that this is your f of t and this is your g of t. When I say t, this is of course f of theta, because here the notion is, here the variable is theta. This is f of theta, this is g of theta. Okay, so we need f prime of theta squared plus g prime of theta squared, the square root of that dt. That's what we need to find, right? Can I find f prime of theta? You just differentiate this one, right? So that is going to be, oh, by the way, what is the lower limit and what is the upper limit? Notice that in a one full cycle, theta varies from 0 to all the way to 2 pi. Remember this angle theta? This angle theta, in a one full cycle, this angle theta was varying from 0 to all the way to 2 pi. Okay, so theta goes from 0 to 2 pi. So this should be 0, this should be 2 pi. All what we need to do is compute this integral. F prime of theta is going to be r minus r cosine theta, whole thing is squared, plus g prime of theta is r sine theta, whole thing squared, the square root of that, d theta. Oh, here it is not t, okay, it is theta. D theta. Okay, now if you do a little bit of simplification, you will see that this is equal to r times 0 to 2 pi. You can pull out the r, 2 pi, 2 minus 2 cosine theta, the square root of that, d theta. If you calculate this integral, you will get 8r. Okay, calculation of this integral, I will leave that as an exercise because we have done these types of integrals in calculus too. Okay, using substitution, you should be able to do this integration and see that its value is 8r. Okay, that's the arc length. Okay, all right, that completes that example. Okay, we are down to the last example of this section. Here is the example. Let x is equal to x of t and y is equal to y of t be parametric equations for a curve C. Show that if x and y are both twice differentiable functions of t, then the concavity at a point on C is given by d squared y over dx squared is equal to this expression. Okay, why do we say concavity? Because concavity is determined by d squared y over dx squared, or the second derivative of the function, right? That's why we say that the concavity at a point is given by d squared y over dx squared. That's basically because we can use this d squared y over dx squared to determine the concavity. Okay, so we need to show that the concavity d squared y over dx squared is given by this expression when dx over dt is not equal to 0. Okay, and we have a second part. Let's worry about that one later. Let's first prove this formula. How do we prove this formula when dx over dt is not equal to 0? Well, we are going to observe a couple of things. Okay, first of notice that x is a function of t, y is also a function of t. X is equal to xt, y is equal to yt. Okay, so we need to find d squared y over dx squared. So here are the things that I'm going to do. First of all, I'm going to find an expression for d squared x over dt squared. Since x is a function of t, this is possible, right? I can differentiate that function x with respect to t twice. By definition, this is nothing but d over dt dx over dt. You take the derivative of dx over dt to find the second derivative, right? So these two should be equal. Now I am applying the chain rule. Okay, so now I'm going to change this variable. I'm going to put the variable x here, and then at the end I'm going to multiply it by dx over dt. I'm applying the chain rule. Okay, direct chain rule. D over dt dx over dt is equal to d over dx, the same thing, times dx over dt. That's what we call the chain rule. Okay, now from this one I'm going to isolate this expression. If I isolate that expression, this is what I get. I divide both sides by dx over dt, then I get this one. Okay, similarly, doing the same thing for d squared y over dt squared, you can isolate a similar quantity. You can isolate this quantity to find that to be d squared y over dt squared divided by dx over dt. Okay, I will leave this as an exercise for you. Now I need all the ingredients I need to find d squared y over dx squared. Okay, by definition, d squared y over dx squared is nothing but d over dx dy over dx, right? You take the derivative of the derivative of y. Derivative of y is dy over dx. You take the derivative one more time to find the second derivative. Okay, so I will leave this dy over dx as it is. Now I'm going to replace this dy over dx by dy over dt divided by dx over dt. That is the definition we had, right? We had that multiple times. We used that definition multiple times. See here, dy over dx is equal to y prime of theta divided by x prime of theta. Y prime of theta is nothing but dy over d theta. Okay, this is dx over d theta. Theta is of course t in this case. So that's what I'm doing here. Okay, so this dy over dx is nothing but dy over d theta dt divided by dx over dt. Okay, or you can view this as, if you want, you can view this as y prime of t divided by x prime of t. That's it. Okay, dy over dx. This is nothing but dy over dx. Okay, now what we are going to do is I'm going to differentiate this. Okay, I'm going to differentiate this using the quotient rule. See, this is your denominator, this is the numerator. If you apply the quotient rule, the square of the denominator should go to the bottom. So I have the square of the denominator here, and then leave this one fixed, dx over dt here, and take the derivative of the top guy. Top guy is the derivative of this function. Derivative of that function is exactly this one, d over dx dy over dt. And then minus, leave the top guy fixed, that is dy over dt, and then take the derivative of the bottom guy, that is d over dx over dt. Okay, remember you are taking the derivative with respect to x. Okay, so this is the formula right now we have. Now we can plug in for these two quantities using the equations that we already found. See, we found equations for these two quantities. This is exactly this. So I can replace that by this expression. This part is exactly this right here. Okay, so I can replace that with this expression. So that's what I do here. I plug in that quantity here and then this quantity here. This quantity. Pardon me. This one is this quantity. This one is this quantity. Okay. So I get this formula. Now I am doing a little bit of algebra. Okay. So here you have dx over dt in the bottom, dx over dt in the bottom. So you have a common denominator, and if you simplify, this denominator will come to the bottom together with this dx over dt squared. That will give you the dx over dt cube. Okay, so that completes the proof. So this formula is valid. Okay, so you can use this formula to determine the concavity of your function, parametric equation. All right, let's go to the second part. Use this result to confirm that the cycloid given by x is equal to r sine theta minus r, x is equal to r theta minus r sine theta, comma, y is equal to r minus r cosine theta is concave down everywhere except when theta is an even multiple of pi. Remember, the shape was again like this, right? As you can see, this curve, this continuous, this curve is always concave down, except at these points. At these points, you have sharp corner here, so the concavity is not defined at this point, right? Except at these points, everywhere else, your function concaves down. Your function is concave down, right? Concave down means, you know from your calculus 1 class, d squared y over dx squared is negative or positive? It's negative, right? Concave down means it's negative. So all what we need to show is to show that it's concave down everywhere except for the even multiples of pi. We need to show that d squared y over dx squared is negative for all theta values, but even multiples of pi. Okay. All right. So how do we prove that? First of all, let's find d squared y over dx squared. Okay. To find d squared y over dx squared, I'm going to use this formula. Okay. Here is the calculation. In our example, our variable is of course theta. So I find dx over d theta first. That is r minus r cosine theta. Remember, equations are given to us. Okay. Here are the equations. You can find dx over dt from this equation, dy over dt from this one. Okay. So if you do that, dx over dt is r minus r cosine theta, and we can also find d squared over dt squared. That is going to be the derivative of this expression, which is r sine theta, the second derivative, right? Similarly, you can find dy over dt, that is r sine theta. If you take the derivative of this one more time, you will get d squared y over d theta, theta squared, which is r cosine theta. Okay. Now I am ready to go with this formula. We know that d squared y over x squared is dx over dt. Remember, this t is in this case, in our case, it's theta. Okay. You should have dx over d theta here, dx over d theta is exactly r minus r cosine theta, and then d squared y over dt squared. Okay, that is r cosine theta. D squared y over dt squared is r cosine theta. That should come here. And then this one, d squared x over dt squared. That is exactly r sine theta. You have r sine theta here. And then finally you have dy over d theta, which is of course this one, r sine theta. And in the bottom you should have dx over dt to the power 3, which is r minus r cosine theta to the power 3. Okay. All right, now it's all about simplifying this expression. If you simplify this expression, you should be able to see that you get this expression. Okay, this d squared y over dx squared is equal to minus times 1 over r times 1 minus cosine squared cosine theta whole thing squared. Now notice that this is negative. This is less than 0 for all theta in R. R is a set of real numbers, except when theta is an even multiple of pi. What happens when theta is an even multiple of pi? Look at the denominator. When theta is an even multiple of pi, cosine theta is always 1. 1 minus 1 is 0. So this expression blows up when theta is an even multiple of pi. But when theta is not an even multiple of pi, always this expression is negative. That means, what does that tell you? If the second derivative is negative, the function is concave. Your parametric curve is concave. Curve of cycloid is concave when theta is not an even multiple of pi. Okay, that's what exactly we were asked to prove. Okay, use this result to confirm the cycloid given by these two parametric equations is concave down except when theta is an even multiple of pi. Okay, so that completes that proof, and with that actually we conclude section 9.1. I'll stop there and I'll see you next time.